I give you another example where I'm taking this from past final exam question. So this is a question in 1415, a long time ago. Question 3b. So the question here is asking for show the given vector field is a conservative vector field, and after that you have to find the potential function and then compute the work done to move an object from some specific point. Okay, so firstly we want to show that the given f, so you have to be careful the way you want to rewrite the vector function given. Okay, so we implement the curl f, and normally in exam the given vector field will be conservative vector field, because there are so many things, there are so many interesting things that can be done afterward. Okay, but then not necessarily always conservative, but yeah, I would say every time the question I mean for the exam 6, so normally the given question regarding this topic, so the F is always conservative vector field, so that there are many things that you can apply all the special property of the conservative vector field and so on. Okay, so now we want to show that the given F is a conservative vector field. So to obtain the curl, then this is the procedure. Okay, so firstly we find the J cross K to get I. So del Y. Okay, you have to be careful when you want to differentiate this. Okay, so Y is inside the exponential function. So when you differentiate that, so to X constant, and then Y plus 2Z, and don't forget to apply the chain rule and differentiate with respect to Y, and you got 1. Okay, 1. Alright, so that is the del Y of 2X Y plus 2Z. Okay, minus, and differentiate this with respect to Z. Okay, minus, so X Y plus 2Z, and then multiplied by 2 because you differentiate with respect to Z. Okay, so next the component J, so K cross I del Z, so you have Y plus 2Z, and then multiplied by 2 minus del X, so you have 2 and since X is only outside the exponent, so you have 2 Y plus 2Z. Okay, and then for the I cross J to get component K del X, so you have Y plus 2Z minus del Y, so Y plus 2Z. So it looks like this one, when you simplify, you have 2X, you have 2X Y plus 2Z minus 2X Y plus 2Z. The second term, 2 Y plus 2Z minus 2 Y plus 2Z. And the last one, Y plus 2Z minus Y plus 2Z. So then, then we can obtain that the curl F is 0. So we can conclude that F is a conservative field. Okay, it's not so complicated, right? But you have to be careful when you differentiate partially. Okay, so next, since it is conservative, then we able to get the scalar potential function, as we know that the given vector field can be written to be the gradient of phi. Okay, so phi x is equal to Y plus 2Z. Phi y is equal to XE y plus 2z, and phi z is equal to 2x e y plus 2z. So we want to get the phi in terms of x, y, z. So we have to integrate ey plus 2z dx. And the second one, phi x, y, z is equal to the integration of x ey plus 2z dy. And the third one, the integration of 2x ey plus 2z dz. Okay, now we have to integrate. So first integrate respect to x, so you will get x e y plus 2z plus a. And then y, okay, you have to integrate exponential function. So x e y plus 2z, and this one is integration. So here you have to know how to integrate that. If you're not sure how to integrate e to the power of y plus 2z with respect to y, so you can our aim is to integrate e y plus 2z, and here 2z is a constant, so with respect to y, so you can assume, so you let u equal to y plus 2z, and now you want to replace everything in terms of u, so you need to find what is dy in terms of du in terms of u. So you have to differentiate u with respect to y, so then we'll give you 1, so you can see that dy is equal to du. So once you substitute back into your integration, so you have eu and dy is dy is du. So when you integrate, you have eu back, so you will get y plus 2z. Okay, so that is how you can obtain this one. So then here you got b, and then the third one you have to integrate respect to z, so to x constant, so e y plus 2z, and then because there is 2 there, 2, and then divided by 2, okay, plus c. Okay, or you can check for the when you integrate integrate because 2x is constant, so we just ignore, so we just focus on integrate the e y plus 2z dz. Okay, so for this we also implement the substitution u equal to y plus 2z du dz is 2, so dz is du over 2. So when you substitute here, you have eu and dz is du over 2. So when you integrate eu du, then you will get eu back plus constant. So the answer is eu is y plus 2z. That's why we can show the answer is this one. Okay, because x is there, so it can be cancelled out, and then we have only x e y plus 2 Z plus C. So they are all the same, right? XE, XE, and this one also XE. So meaning that the scalar potential function that we are looking for is, because they are the same, you just take one of them, where we have XE, Y plus 2Z plus D. Okay. So you can check whether your answer is correct or not. So by find the partial derivatives back. So phi x differentiate phi x, so you will only have e y plus 2z, and phi y, you have x e y plus 2z. Phi z, you have 2x e y plus 2z, and it is the same. This is for checking only, okay? So you don't need to provide in your calculation, just for your own sake, just for your own satisfactory. Okay, so if you check, the answer is the same, right, as this one. This is from the vector field given, and they are the same. So meaning that your result of the scalar potential function that you are looking for is correct. Okay, so now next we look at another question. Find the work done. Okay, find the work done. So we want to obtain the work done. So what is the formula of work done? So work done, if your given function here, the vector function here is a force field, so the F dot dr here is actually the total work that the object has done, okay, along the C. So now because it is so now we want to check. So if it is looks like that you want to go to 1 0 minus 1. So you want to, from this point, so you want to go 0 0 0, and then from 0 0 0 you go to 0 1 1. Okay, so meaning that your initial is this one, and this is your terminal. So this is your A, and this is your point B. Okay, so it looks like you can evaluate the work done. You can use the fundamental theorem of for line integral from the point A to the point B. Okay, just like we can say we do a shortcut way using the fundamental theorem for line integral. So what you have to do is you just replace the point B minus replace the point A into your scalar potential function. Okay, so now what is your phi? Your phi just now, okay, so you have x e y plus 2z plus d. Okay, that is your scalar potential function. Okay, so my iPad frozen. Can I increase? Okay, so then we substitute for the given point B 0 1 1. So x 0, so everything 0, right? So x 0, so 0 plus d minus, and then you replace 1 0 1. So 1 1 e, okay, 1 e y 0 minus 1. So 0 plus 2 minus 1 plus d. Okay, so what you can show here, you have d minus d minus e minus 2. So what you have obtained is minus 1 over e2. Okay, so that is your work done. Simple, right? So just checking. So your phi is x ey plus 2z, and when we substitute the b, because your x is 0, so your x is 0 and this one is 0, so everything 0 and just plus d minus. So now your x, the point A, your x is 1, y is 0, so y plus 2 minus 1. So you have e minus 2. So the d gone, and then you only have negative 1 over e to the power of 2. Okay, so that is the total work done.